Good afternoon, everybody. Welcome back to my series on why I wire data and my what happens when you type www.google.com in the browser. This is going to be on TLS encryption, so we're going to get started pretty quick. This is based on the third in a mini series that I kind of started earlier on YouTube. And this is actually a big one, so I probably am going to have to break this up into several parts because I don't want to do like a 2-hour long video for everybody to watch because you get bored and frankly go away. So I'll do my best to go through this a little bit at a time and break it up a little bit. But it's based on the interview question, what happens when you type www.google.com in the browser from a TCP stack perspective. And we've kind of already walked through the name resolution process, and I've got more to do on it because I want more tie-ins and there's more things that people need to understand. Talked about the TCP three-way handshake that's already out there. Tonight we're going to talk about the TLS handshake and why it's so important to understand how it works. And then the next series, or the next one I want to do is on HTTP, the request and response, and then maybe on something on finishing up the whole process. But we're going to kind of talk about several different things as we go through, and I think it'll be pretty cool to see what happens with this one. So TLS encryption is just that. It's encryption, guys. I hear it all the time. I've actually seen posts where people talk about they need to understand the certificate chain for authentication for when you go to your bank or go to a website. Well, the truth of it is we're not really authenticating. We are validating a trust that that certificate was issued by a trusted certificate provider, and we'll get into that a little bit. It's not signing either. It's not signing any of the data to say this data hasn't been changed from when you sent it up to when it came back. That's a separate process. So notice most of the time when you go to your bank, it doesn't let you in. It encrypts the channel. Even when you go to Google, they're encrypting data now. So when you go to Google, but there's no authentication process that takes place. And when you go to your bank, you notice that you have to type in a username and password or something to that extent. So it's not really authentication. And like I said, it's not signing. It's simply hiding what is being sent or received. It's encrypting it in a way that only the other side can decrypt it, or so we think. So that's the whole point of TLS. TLS is based on a trust. We're trusting that your machine has something on it that's going to trust the provider of that certificate. That's why when you buy a certificate from Thought or DigiCert or somewhere else, you go through a process of verifying who you are. You might have to put a record in your DNS to show that you own DNS. You might actually have to have your information in a Dun & Bradstreet, but there's multiple things that happen in order to verify who you are. So that means the issuer is vetting people that order the certs, and your machine trusts those vendors as a part of the bigger process. More advanced certificates are vetted more. They're vetted more, i.e. Dun & Bradstreets and other methods to see who you are. They call your company and see that you actually or call to a public line and see that the number can be transferred to you, and you verify that you're an employee of the company when you order those certs. So a lot of things happen to make sure that trust is not broken somewhere. Your machine has a trust root store with a public certificate for all the certificate vendors it trusts. You can remove all those and make it so you don't trust them, but that's a whole nother story. But that's part of the process, is how it begins with that trusted root. And so you have a root certificate store. And in this root certificate store, this is out of a Windows box. This has all your root certificates in it that machine trusts. Hidden some because they're related to a domain that I'm currently on. But this is how this whole process starts that verification. And we'll kind of go into more detail about it. But you need to understand this. This right here is the actual certificate chain. And so the root certificates are usually kept offline, and that's why it's important to understand how that whole chain process works. So you can see that right here is the root certificate, and right here is what's called an intermediate. Now, what's interesting is a lot of people think that intermediate is actually stored on your local machine, but it's not. You actually get the intermediate is sent down from the server if it's set up correctly, and that's a whole nother ball game that I want to do a separate video on and talk about. But you have to understand there is a chain to this whole process, and we'll get more into it. But that's what you're trusting, is you're trusting the original provider, that certification path. And that's what's saying, okay, I trust the certificate that's come down to me. I'm going to use that public key to encrypt my data when I go up to www.google.com. So here's the important part. The steps of a good TLS handshake is really oftentimes misunderstood or not thought about. In doing a lot of performance testing, this is something you have to understand. Because remember, we talked about your DNS lookups and how that could take time out of the whole entire transaction. Then you have the TCP set up, and that could take time out of the entire transaction. And then if you have to do a TLS handshake, that takes time. And so that adds to your entire transaction. And during any part of this process, if it fails, your application may time out or fail depending on how your application works and what kind of recovery methods it has in place. So steps of a good TLS handshake have to complete in 15 seconds. That seems like an eternity. And to be honest, it is most of the time. Most of the time, these are done in milliseconds by the time it does all these steps. So you have a client hello, client says, hey, let's talk. And during that client hello is when it passes what cipher suites are allowed for it to use. So it may pass like 20 or 30 cipher suites that it can use. The server hello returns a reply back and says, that's cool, I want to talk to you, but we're only going to use this cipher suite. So it picks the top out of its list and verifies it has the same thing as what you have, and it connects up, right? It says, here we go. This is a failure point because if you don't support the cipher suite that the client is connecting with, or vice versa, the server doesn't support any of the cipher suites that the client offered, this is a failure point. And so it can fail right there. So then the server sometimes will provide the certificate in that hello. So you might have the certificate server hello and done portion. This is where it sends that down to the client, what certificate it's using. After that certificate comes down, then the client has to do several things. And this is where I see people make a mistake when they're doing traces, is oftentimes they'll trace just between client and server. But what people don't realize is that client has to make calls out to many things. Name check does the URL host name. Make sure that host name is either in the host name of the certificate or subject alternative name. Or if there's a wildcard, does it match within the host? And I'll get into that more in depth in a different video. It does a certificate trust chain check. Does it trust the root certificate, and did it get the intermediate cert from the server? So does it have both of them? And it has to check both of them to see that both of those are still valid. Does a date check, and then it checks the certificate revocation list, or CRL, or OCSP check, and those go out to separate websites. So like if it's a DigiCert cert, it will go check the OCSP at DigiCert. So this is where just tracing between the client and the server, you may not see that connection take place, or you may not see it fail. It's kind of important to think about that. Okay, those things come into play, and it can slow down the whole process. Then you have the client key exchange. This is where we're changing the cipher spec generally from a private public key pair to a symmetric key pair, because asymmetric key exchange is expensive, it's costly, it takes more CPU, and then we renegotiate or we pass our symmetric keys between each other using the public-private key pair, and we're going to change and go to a symmetric key. So this is important. This is where we have cipher suite failures in a lot of cases. So you need to know that. It finishes changing the cipher suite, and then maybe it's done. We hope it's done. And we connect up and start passing that data back and forth. Interesting thing is there's TLS codes that are available, but guess what? They're encrypted, so you don't even get to see what the failure is if it fails. Kind of scary. Makes it difficult to troubleshoot. Must complete in 15 seconds or less. Most browsers time out in 30 seconds. That handshake really is important to understand and know that it can be the cause of why applications don't connect up or failures along the way. So it's important to be able to understand this process. Here is a Wireshark with just a high level TLS exchange, right? You can see the three-way handshakes takes place here. So that's TCP three-way. Then you have the client hello that takes place. You have the server hello that takes place. Then you have the server that's passing the certificate down. Now, in between this right here and the client key exchange, that PC is doing an OCSP check, and it's checking the date and time, and it's checking the chain, and it's doing all those other things in between those two spots. It's got a lot to do in between there. And so you can often look at some timings and see if there's a problem between there. Then here's where it finally agrees and says, hey, we agreed on the cipher suite. We are changing over to our symmetric key exchange. And then we should see application data being passed. That's what we want to see. But it all needs to complete in 15 seconds. So keep an eye on that. Otherwise, you probably have a failure. If you get a failure back, you may see it one side send a finish or a fin command. And when it sends that fin command, it'll also usually include an error code. And oftentimes it comes back with a 255 error code, which means it's encrypted. Can't see it, guys. That can be a problem for you. So difficult to troubleshoot. But again, really cool. Now think about it. If I have all of this information and I consider this my handshake, wouldn't I want to pay attention to the times on this? I would. So here we're doing that at scale. We're looking at the handshake and we're seeing how many connected sessions. This is in RevealX. Very cool tool. We actually do some decryption. So this is RevealX doing some decryption for us and telling us it's decrypting some of those sessions. May not be all of them. There's several reasons why it may not be all of them. That's a whole different piece. But it's telling me that some of those will be decrypted. So 495 sessions are decrypted. Cool. Out of 1,247. Any resume sessions? Oh, that's a good one for another video. What happens on resuming a TLS session? Does it renegotiate? Good question. Anything with weak ciphers, man, all this stuff that's going on nowadays, everybody's got to make sure their ciphers are up to date and we're using the good stuff. That's pretty important. So I'd like to know that. And then we have this cool thing called aborted sessions. And the cool thing is that's aborted in the middle of the handshake. So if you see aborted sessions under this counter, this is kind of important to know. I aborted during my TLS handshake. And it starts figuring that out fairly early on, shortly after the client says, hey, client hello. It now knows, even though it's not coming in on 443, it doesn't know it's going to be an HTTPS connection, a true TLS connected session, until the client says, here you go, let's start. So that's when, anytime after that, that this aborted will show up. Pretty cool, at least from what I've found doing network traces and verifying this. Could be wrong, and maybe somebody from XtraHop might jump on and tell me, that's not correct. We start when the 443 starts of the handshake. But from what I can tell, it looks like an aborted session actually is aborted after it sends the client hello. So if you get through the TCP three-way and it quits at the TCP three-way before the client ever says hello, that will show up usually under the TCP three-way aborted sessions. Good to know, good to think about. And I hope I'm right. And if I'm not, somebody punch in there and tell me. I'd love to hear it in the comments. Make some improvements on the video. Second piece of this that's really important is this SSL handshake time. And when I got to looking at this, a lot of the things put averages in there, but I really don't care about the averages of my SSL handshake time. What I care about is my maximums. Because if I've got anything going longer than 15 seconds, I've got a problem. So those averages throw you off. So I'm just really concerned about min and max, and I could add the min and max in here if I wanted to. But my biggest one is maximum. So if I've got a problem going on, I can look at this dashboard and go, it definitely has nothing to do with TLS. I don't have any aborts going on. I don't have any TLS handshakes that are taking a long time. Those things are quick and easy. And I can set it up for individual URLs. I can get this SSL information based on individual host headers. So in this case, this is for a specific vendor that I'm actually measuring this for. And so we can see the handshake time by server. In this case, we're only connecting to one IP. If there were multiple IPs that we're connected to, I could see that as well. Again, really cool that I can measure this. Any alerts that are coming through that might be important, even if it's that 255 alert, that would be nice to know, right? Because it tells me something happened, but I don't know what it is. I also get the TLS version. So I know all the connections to this customer or to this vendor are actually TLS 1.2. I've got no questions about it. I can look back a week, 10 days, 30 days, 60 days. I know that. So when somebody says, hey, you've got to be sure we're using TLS 1.2 or we're going to turn off TLS 1.0, I can go, I'm not worried about it because I already know our critical vendors are all using TLS 1.2 and we're negotiating correctly with them. See the cipher suites down here? I've kind of got it covered up by my video, but it tells me what the top cipher suites that are being used. That's important as well. Could they be older cipher suites? Could they be cipher suites that have risks or problems with them? Absolutely. And then the top SNI domain and the expiration date on their certificate. I get all of that information all at once, right? So this gives me data about vendors we connected to. I can do it within applications. So say Exchange or SharePoint. I can get all of this data within those type of events rather quickly. So pretty cool stuff. I like it a lot. And so I actually use this way more than I probably, well, I think it's way more than I probably should, but I really like the fact that I get this data quick. And oftentimes it helps me troubleshoot because I do it just like the actual dashboard that I have has DNS at the top, shows me how many DNS queries, whether I'm having problems with DNS queries, then it goes right into the TCP three-way handshake, and I see the three-way handshake and the TCP latency, and then it moves right into the SSL handshake, and I can see the timings on the SSL handshake and any aborts or any problems that I'm having with the SSL handshake. Boom, and then if I'm decrypting anything that's going to anybody internally, I can actually take and put the HTTP there and see what the information is about the HTTP, the errors, those kind of things. Cool thing is if I'm decrypting, this whole SSL handshake, whoops, not that one, this one right here, it actually gives me really good information when I'm decrypting that because then I know that what kind of TLS problems there are. So again, pretty cool stuff. So I wanted to bring up more about the online certificate status protocol versus certificate revocation list. I'm going to do a separate video on this, but this is kind of the quick and down and dirty on OCSP versus CRL because it's one of the things that slows people down a little bit. I've got to check that OCSP, so I've got to validate that certificate and see that it's still good. So OCSP says, hey, all I've got to do is pass up to an HTTP website, the OCSP information and the thumbprint of the certificate that I'm checking to see if it's still good. And if it turns out yes, then I can move on with my certificate handshake. Certificate revocation list, I might download once a day once I connect to it. And so that really creates some additional problems. And some certificate revocation lists can be really, really long and really big. So that can be another issue that people might have with it. But I've seen problems with OCSP for different vendors. And when I do, I oftentimes see the handshake hit 15 seconds. And so that's something you need to be paying attention to and monitoring quite often. So I'm going to stop this video here. I'm not going to go any further. I'm going to leave you kind of hanging on purpose because there is so much more data you can get out of this and so many more things that you can do with certificates. I want to just keep it as short as possible. And this is running almost 20 minutes. So I'm going to stop here and I'll dig more into this over the next couple of weeks. I appreciate your time. If you get a chance, please subscribe. Say hello, and leave comments. That's the biggest piece. If you got questions, ask. I'd love to hear what other people think. And if you think I'm wrong, tell me. I'd love to learn. The more I can learn, the better I'll be. So I appreciate your time. Thanks for stopping in. Hopefully it's of value to you, and hopefully it provides some benefit. You guys have a great day.